Hey guys, I'm back. I'm trying to start a new series of videos, mostly about the physics news that break out. My plan is to try to explain what's going on in the world of physics. Because what I realize is that most of the time, these big news make their way to big news outlets and uh, more often than not, they are not well understood and they are being thought of something that is completely irrelevant to the actual research that is done. So in these videos, I don't know how often I can make them, but I'll try to explain as much as I can and I understand from that specific research that makes it all the way to you know to news to hopefully try to basically minimize or help a little bit this misunderstanding that we have sometimes from what we see on the news. Okay, so very recently, if you're aware, we had a big discovery about dark matter, right? So scientists basically claim that, let me go back, claim that they found half of the missing matter, right? So this dark matter thing, and I'll get to what dark matter is in a couple of slides, in actually one slide. So in these three, well-known news outlets, we have three big headlines about this discovery, right? Half of the universe's missing matter has been finally found. New Scientist says, and Science Alert says, astronomers have finally found most of the universe's missing visible matter. Futurism says, scientists just found half of the missing matter in our universe. So these are really big headlines, and let's see if we can understand a little bit more than what is, what trying to explain in their blogs here. All right, so let me start with the question, what dark matter is. Where is dark matter coming from, right? What is this thing? Dark matter comes from a discrepancy in velocity of rotation at the edge of galaxies. What does it mean? So let me demonstrate with a video that I found on Wikipedia. So on the left-hand side, I have a galaxy that has dark matter in it and is actually consistent with what we observe actually in the universe. And on the right hand side, there is no dark matter, right? And we are basically following a classical theory, right? So let me play a video. So you can see what's obvious is that the galaxy on the left hand side, which actually is observed, the stars in the galaxy, on the wings of the galaxy, are rotating much faster than this galaxy that follows the classical theory without dark matter, right? So this makes you believe that dark matter exists, right? Because this is consistent with what we observe in the universe, and at least that's the most likely, scenario that dark matter exists until we find a better theory, right? That's how science works. All right, so let's take a look at the velocity profile of these galaxies versus distance from the center of each galaxy, right? So distance, if it is 0, means that you're at the center of the galaxy, either of them, right? And then the further you go from the center of the galaxy, the more the larger the velocity of the stars will be. So in both models, right, in both of these, galaxies, the velocity increases as you go away from the center of the galaxy, and then it's a pretty dramatic increase in the velocity. And then in the model B, which is a realistic model, the velocity pretty much stays constant throughout the galaxy. And in model A, which is a classical theory, which we do not observe actually, the velocity of these stars drop pretty dramatically as you go further from the center of the galaxy. All right. So let me ask, what is the problem here, right? So there's some inconsistency in the theory, right? So the problem is to make physics agree with what we observe. Um, we need more than 10 times more matter in the, you know, we need 10 times more matter that we can see, right? In other words, we're not seeing more than 95% of matter in the universe. In other words, so most of the matter is invisible to us, right? The matter that we observe with our telescopes, it's not enough to make the galaxies work the way they are supposed to. And this is a huge problem, right? You're missing 95% of the matter. Okay, so you can imagine why these kind of discoveries make headlines, right? Because this is a huge deal for physics today. All right, so let me go further. So let's look at these headlines again. Now they kind of make more sense, right? Why they are kind of like big headlines. All right, cool. So let's get to the heart of the matter. How did scientists find, the other half? How did that happen? So basically, a couple of scientific papers came out very recently. First one, September 15 of this year, 2017, and the second one within a couple weeks, 29th of September 2017, right? So there's only a couple weeks, time difference between these two papers. So I bet what happened was, first the UBC team published their paper, and then the Edinburgh team was working on the same subject, and they were like, "Oh man, these guys came up with with a paper, and let's write it up, let's submit it." And I really feel bad. Most likely, Peacock is the PI, and the rest are like postdocs or graduate students, and I really feel bad for them. Within these couple of weeks, they probably were under quite a bit of pressure to push the paper out. So anyways, yeah, these are the two papers that recently were published, and you can go check them out. Definitely check out archive.org if you haven't seen it. If you're in science and computer science, there's a pretty good chance that you've already visited this website. And it's a great way of basically getting free papers, free publication before they are actually published in a scientific journal, right? Okay, cool. So let's go ahead. So what are they saying? What are these scientists saying, basically? The unseen mass can be from very hot atoms that move around the galaxy, right? That's basically what they are claiming in these two papers, right? And these two papers are pretty consistent. They are getting pretty close results. And we will know why, because they use the same source of data, and fortunately neither of them made a huge mistake. Okay, so these scientists are saying that this extra mass is due to really fast oxygen or atoms that are moving around in and out of galaxies and around galaxies, and we cannot see them. They are basically invisible to us. And why don't we see them? Because they don't interact with light, or at least visible light, as much as the other reason is that they are very dilute, right? We were talking about 100 atoms in a cubic meter. 100 atoms in a cubic meter. This is super dilute, guys. Like only 100 atoms in a cubic meter is like next to nothing, right? Okay, so why don't they interact with light as much, you ask? Because most of these atoms are basically, the electrons are stripped off, so it's better to say they are ions, right? So since they don't have as much electrons as they have protons, they are basically ions. The other, so the other reason, as we discussed, is that it's really dilute. So there are not a whole lot of photons, relatively speaking, out there to hit these atoms and scatter. So the art is somehow find an interaction between these ions, or these ions, yes, it's better to use the right word. These ions and photons, right? So, how hot are these atoms, right? I mentioned that these are hot atoms. Researchers say these are about 100 million kelvins. 100 million kelvins, right? So that's 10 to the 8. These are smoking hot atoms, by the way, or ions. So the hotter an atom or an ion is, the faster it moves. So how fast do these atoms move? These ions move about 400 kilometers per second. 400 kilometers per second, which is equivalent to 800,000 miles per hour. Just remember when you drive really fast, like 100 miles an hour, and you feel that you're driving really fast, right? Better not to do that anyways, but 800,000 miles per hour. So, all right, just saying, it's pretty fast. All right, so how long does it take these atoms, or ions, oh man, I should say ions, I keep saying atoms, but yeah, okay, anyways, you know what I mean. How long does it take them to travel across the galaxy? So I did a rough calculation. It's about 75,000 years, right? Let me show you real quick how I did this calculation. All right, so we know that the galaxy, the Milky Way galaxy, is about 100,000 light years. And this is, by the way, Google. You can do your calculations on Google, and it's really fun. C, Google recognizes C as the speed of light, 365 days per year, and then 25 hours per day, and then 3,600 seconds per hour, right? And dividing that by 400,000 meters per second, which is 400 kilometers per second, gives you 75 million years. 75 million years. That's a lot of years, right? Okay, so let's go back to our presentation. Okay, yeah. All right, cool. So let's go to the next slide. So, how did these researchers, come up with this idea? How did they draw these conclusions, right? So they used a Sloan Digital Sky Survey, SDSS, in short. And this telescope has a really fancy camera. Every single of these, squares, there's a fancy CCD, cool to really cold temperatures, and very fancy, very high quality built, CCD cameras or sensors. And in front of them, there is a filter, right? Because you want to look at different wavelength of light, right? So, for example, the first one looks at red, the other one looks at a weird color, which I cannot tell, blue, and green, all these different colors, mostly because I do not know what exact color that is. The colors that I know are red, green, blue, yellow, brown. That's my vocabulary, guys. So I'm sorry about that. Anyways, so, and these are the wavelength channels of these different filters, right? So it goes from deep blue and, ultraviolet, not way into ultraviolet, but that's pretty decent, 300 nanometers. And it goes to 1 micron in wavelength and all the way to 1.1 micron, right? 11,000 angstroms. And then the cutoff is basically silicon band gap, right? You cannot push, silicon semiconductor based image sensors anywhere, beyond 1100, unless you do some fancy techniques. Anyways, so what they did is phenomenal. They surveyed 260,000 pairs of galaxies, right? 260,000 pairs of galaxies. And by the way, this data is available to you for free. Just go ahead and search for Sloan Digital Sky Survey, and you can download the data for free and start researching on it if you like. So, anyways, just saying. So, what they did, they looked at all these 260,000 pairs of galaxies, and they used this. I'm not even sure how to pronounce this. Sunbayev Zeldovich effect. So they get the data, they filtered it with this Sunbayev-Zeldovich effect analysis, right? What is this effect? SZ, let's call it SZ effect, is that low energy photons, right? Oh, there's a mistake there. Anyways, low energy photons interact with fast electrons, right? And they gain energy from the electron. So what happens is that the electron borrows some energy to this low energy photon, and therefore the photon becomes more energetic, therefore it has a lower wavelength, right? So the more compact, the more energetic a photon is, right? In simple terms. And the electron becomes slower. So basically this arrow, it tended to show the velocity of the electron. Anyways, so since they know this effect, by looking at the data from the telescope, they could say, okay, so actually there is so much amount of matter around, hot atoms or hot ions around these galaxies, right? Okay, so let me move myself a little bit up here. Every single time I have to move myself in these videos, so I gotta think of a way of not having to do that. Anyways, so after they did all kind of, in data analysis, filtering, and, very careful, playing with numbers and simulations, they basically came across this delta y parameter, which is basically close to like an optical depth. That the larger delta y is, the larger density of these electrons are, right? It basically tells you how much the energy of a photon changes, right? If you're closer to, this is a heat map, right? The hotter it is, the more energy change the photon is, and there is higher density of these fast ions, right? Oh, I made it. I finally said ions instead of atoms. All right. Anyways, so that's it for today. This is a very long paper. I suggest you go ahead and take a look at it. Just for no reason. Try to get a feel for those numbers. The most important thing is that don't be afraid to fact check things. Just go ahead, trust yourself, look at those numbers, look at a few Wikipedia pages, ask friends, ask me, leave a comment under this video, and I'll try to answer as many questions as I can. And don't be afraid, you'll learn. It's how it works. All right, cool. So see you guys next time.